Okay. Yeah, so hi everyone and welcome to the second MLFL talk of this semester. This week we are very excited to host Professor David Harwath. Professor David is an assistant professor in the computer science department at the University of Texas, Austin. And his research primarily focuses on multimodal learning, where the modalities typically are speech, audio, vision, and text. His work has been published at a number of top-tier venues such as NeurIPS, ACL, ICASP, ECCV, and CBPR, and it was also nominated for a Best Paper Award at ASRU 2015. Prior to joining UT Austin, David was a research scientist at the Spoken Language Systems Group at MIT CSIL under the supervision of James Glass, with whom he also did his doctoral thesis. His doctoral thesis introduced models for the joint perception of speech and vision, and it was awarded the 2018 George M. Sproul's Award for the best PhD thesis in computer science. Before joining MIT, David did a bachelor's in electrical engineering from UIUC. So without further ado, let's get started. Let's all unmute ourselves and welcome the speaker. Okay, yeah, so let's just get started then, yeah. David, on to you.
Okay, thank you very much for hosting me today at UMass virtually. I'm very excited to be here and talk about the work that I've been doing in learning spoken language through vision. So I think that if back on.
I'm getting a cloud. Okay, yeah, we can just go
Okay.
ahead. I think it's a cloud error, yeah.
Okay, so a lot of my inspiration for getting into speech recognition and AI in general has come from classic science fiction movies and books and TV shows and things like that. And I think that it's very interesting that in a lot of from everything from Star Trek to Futurama and Star Wars, 2001, WALL-E, a lot of the most compelling and famous sort of long-lasting memorable characters have been robots. And these robots have all shared a really interesting property, which is that they're all able to communicate with the human characters using spoken natural language. And so I think that it's really not hard to see the influence that these artificial intelligences that have the ability to communicate with natural language have had on the products that are so ubiquitous today. Everything from Siri to Amazon Echo, and I imagine that most of the people watching this talk right now have either on the desk next to them or in their pocket a device which is capable of performing speech recognition. So this was once upon a time a science fiction pipe dream, but it's really become a reality that's part of our daily lives. And the story of how we got to that point is really, it's decades long. Speech recognition research started in the 1950s, 1960s is when people really started first looking into how you could solve this problem. And many thousands of researchers have invested their entire careers in basically trying to push down the word error rates of these recognition systems to the point where they are usable by everyday people in everyday life. And so this is just a graph of part of that history going back to about 1993, showing this steady decline in error rates of speech recognition systems across various tasks. And you can see, in the right-hand side of this graph, since about 2009, 2012 is that period is sort of when neural networks really hit the speech recognition field. And so that's kind of pushed these error rates down into what people are now calling human parity. So sort of 5% and under error rates are where people have kind of decided that these systems are on certain data sets, certain tasks, making the same number of errors as a human would make on a particular data set. But that progress is really amazing that was made over the past decades. But the paradigm that we've actually been following all that time has not really changed in 4 decades. So long before sequence-to-sequence neural networks, were sort of a mainstream thing, speech recognition researchers were essentially following the exact same learning paradigm, where the whole idea is you've got these training examples, which are comprised of a speech recording where somebody recorded themselves speaking some words, and then a transcription in the form of a sequence of words with start and end timestamps. And so you can think of this word level transcription as kind of like a string with colored beads on it, where every single different bead represents a different word. And the training problem is to build a model for what the speech waveform looks like at a particular moment in time where it's covered by a particular colored bead. And then in testing, what we basically do is we do decoding, where we just try and estimate the most likely sequence of colored beads for a particular speech waveform that was observed during testing time. So this approach works very, very well when you have very powerful models and massive amounts of transcribed training data, but it is not at all how humans learn speech. And so the cost of actually producing these waveforms and corresponding transcriptions is so immense that out of the approximately 7,000 human languages spoken throughout the world, we only have ASR technology for about 100 of them, give or take. So an ability to learn in a much less constrained way would really be a game changer for speech recognition technology. And I would argue that this is really just kind of a special case of a much more general fundamental challenge for AI systems in general, which is the fact that most of the highly successful algorithms that we have right now, regardless of your domain, are supervised algorithms, where the input and the output are a priori specified by the model developers. And then we use those to construct this black box model in the middle. But the moment that you break any of the assumptions about the training distribution or the output ontology that you'd like to predict, the models tend to become very, very brittle and break. And in order to port them to a new training domain, you basically have to sort of reinvent the wheel and collect a whole new set of data and label it. And it's enormously time consuming and expensive. And so I think that there's really strong reasons for us to try and work with raw naturalistic data that's found in the world that doesn't require us to heavily annotate everything that we feed to our models. So to hopefully motivate you into thinking that this is a worthwhile thing to do and maybe make sense, I'm gonna play a quick video that depicts how pretty much all of us learned to not only read but also speak and understand language.
In the summer, I like to lie in the sun and watch the birds. And I like to watch the frogs in the pond. Then I curl up in my hollow tree and dream about spring. The end.
So I won't finish out the video because it's just a little bit more crying, but you can see that even though humans like this child, they don't require the kind of supervision and the training labels that our machine learning models do, they still require some kind of training data, and they get angry when you stop giving it to them. So this plot here sort of encapsulates a spectrum of learning paradigms where you can characterize the trade-off between technical difficulty or sort of the onus that's placed on the model to figure out its own sort of its own sort of scheme for characterizing the data versus the amount of human expertise that actually has to go into defining how the data should be represented. So very classical speech recognition learning paradigms are in the upper left-hand corner of this plot, where the idea is that you would actually have trained humans, in many cases highly trained linguists, analyzing recordings of speech and marking down exact start and end times for particular phonemes in the speech signal, and defining phonetic pronunciation dictionaries, and building very, very large language models from lots of text data. And then we would use all of those sources of constraint and supervision to build models that we could use for speech recognition. And in the past several years, especially, we've been starting to move much more towards what I would call a data-based paradigm, where we don't really rely so much on expert linguistic knowledge as much as we did in the past. And that's a lot of that is made possible by advanced training algorithms and deep neural network architectures, where really now we're just kind of at the point where to build a speech recognition system, you just need to have speech and then parallel text transcriptions. But this is still very, very, very expensive and difficult to produce for a new language or a new domain with new vocabulary. And you can go much, much further down to the lower right hand of the spectrum, which is mostly where I work and where I'm going to be talking about today, which I would say is much more close to the closely related to the way that we think humans learn, where in the sensor-based paradigm, you really only have the inputs coming from your speech and your hearing and your vision, and you could imagine you could generalize this to tactile sensing and things like that as well. But today I'm just going to be talking about speech, audio, and visual imagery. So
David,
yes.
we have a question.
Yes.
Subhendu?
Yeah, hi. Looks like I can unmute myself. So I have a quick question about your thoughts on the ASR systems. So I've been working on this more recently. I don't know. I know traditionally it was done in a pipeline system where you had the phoneme corrections and then you had the language model on top of that, and it was pretty complex. And you needed supervision at each step. But more recently, I think the end-to-end models are pretty popular. So I guess if you just have a transformer or encoder decoder, and your input is just an audio sequence, people have been getting almost state-of-the-art results with just using that setup. And all you would need in that case is just end-to-end data, right? So would that still be considered, as requiring a lot of human expertise, you think, or?
Yes, so that would be the data-based paradigm, sort of in the middle here. And those systems generally still do require many, many thousands of hours of transcribed speech recordings in order to get state-of-the-art performance. And so for that reason, it is still incredibly expensive to collect that kind of data. Any time that you're really requiring sort of text transcripts for many thousands of hours of speech gets to be the point where the expense is pretty significant. So it is definitely, it's better than sort of the very highly expert-based systems that we had decades ago, but it's definitely still very expensive.
Okay, all right, thank you.
And in terms of the flexibility, those systems still can't really effectively kind of learn continuously in an online way. You can't just talk to them and teach them new words. You have to teach them new words and new vocabulary. You have to collect new data with those new words and transcribe them and retrain the whole system.
Yeah.
So the paradigm that I want to talk about today is it's a little bit different because it doesn't use any kind of text transcriptions or linguistic labels or anything like that. The idea is really just that we're going to have pictures, just raw RGB pictures, and we're going to record people talking about them. And the idea is that if we can build a model which is able to relate the waveform to the image, then the model must have implicitly learned to do three things. So it must have implicitly learned to recognize some of the words in the speech, the objects in the image, and then to resolve the grounding pattern between them. So it's really trying to use grounding as a surrogate or an alternative for conventional annotation. So the outline of today's talk is I'm going to start by just talking about the models that we actually use to do this kind of cross-modal grounding-based learning. And then I'll talk in the second part about how we actually can recover emergent linguistic structure from the intermediate representations learned by these models. And then finally, I'll talk about applying them across multiple languages and talk about how you can actually learn cross-lingual semantics and visually grounded translations directly in the speech signals using these models. So like I mentioned, our data is very, very similar to captioning data that has been widely explored in the vision and language community. But unlike that data, which has generally the language takes the form of text captions, ours is actually a speech signal. And so there's several key differences between speech signals and text. Namely, we don't have white space separating the words in the speech. So we don't know where the words start and end. We don't even know how many words are in a given speech signal without having a transcription. And also, every single time that you see the same word spoken in two different waveforms, they're going to have completely different waveforms. So that's arising from differences in recording environments and background noise, and differences in the speaker characteristics, because every single different person has a different sounding voice. And even when just you have the same person saying the word meadow twice, it's going to be a different waveform. It's not going to be exactly the same length. There's all kinds of subtle differences that are going to manifest in different instances of that same word type. And so if we wanted to discover sort of the words, in the speech and then ground them into the image, it's in some ways a much more difficult problem than if we just had started with text. But if we can solve it, then the idea is that implicitly we have a model which has learned to do some kind of form of primitive speech recognition. So that's what we're going to really cover today, is how we're actually able to solve this problem. So when I started working on this problem, there weren't any data sets out there that had spoken audio captions for images. So we turned to crowdsourcing on Mechanical Turk, and we started with the MIT Places image classification data set. And we took about 500,000 images from that data set, put them up on Turk, and then we just asked people to describe the content of the images. So we chose Places instead of something like ImageNet, because these image scenes tend to be very complex, and instead of just having one highly salient object sort of in the center of the frame, there's a lot more for people to be able to talk about. And we didn't give the workers on Mechanical Turk any kind of prompt or instructions about what they should be talking about. We just told them to describe what they saw in the image and what they thought was salient, as if they were describing it to somebody who couldn't see the image, maybe over the phone, or somebody who's visually impaired or something like that. So I'll give you an example now of just what these captions sound like.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blueprint dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
So the next step was figuring out how we should exactly model this data. And so there's many different ways that you could imagine trying to build a grounding model for this kind of data. But the ones that I'm going to talk about mostly in this talk today are just very simple convolutional two-stream networks, where you have some kind of image backbone and some kind of audio backbone. So we're representing the image as just an RGB pixel array, and the speech as a spectrogram. So you can kind of think of it as a 2D one-channel image, where each time frequency bin in the spectrogram essentially captures the amount of acoustic energy that's at a particular frequency at a particular point in time. And this is a standard representation that we use for the front end of speech recognition systems. So we're going to have convolutional networks that compute a feature map for both the image as well as the spectrogram. And the idea here is that instead of producing just a single embedding representation for the entire image or the entire spectrogram, these feature maps should preserve something about spatial relationships within the image and something about temporal relationships within the speech signal. So these output tensors here then are on the image side. I'm just showing for this particular network, you're going to have a 14 by 14 grid of 1024 dimensional embeddings. And then on the speech side, we'll have 128 frames of 1024 dimensional embeddings. So the embedding dimension isn't important. What's important is that it's the same across the modalities. And so we're actually able to do some kind of similarity computation between a particular image region and a particular frame in the audio representation. So we're going to do an exhaustive sort of kind of an outer product between these representations, and that's this red density tensor that I'm showing on the right. So we call this a match map because what it does is it basically tells you at a particular point in time and a particular spatial location how much affinity is there as judged by the model. So here what I'm showing is high affinity is red and low affinity is white. And so the idea is if somebody had described the girl or the lighthouse at a particular point in time in the speech signal, then I would want those image regions to have a very, very high affinity score, and then all the other image regions to have a low affinity score. So the question then becomes, how do you actually train the model to predict a match map that makes sense? Because we don't have any kind of ground truth alignments for which piece of audio describes which piece of the image. So instead, we're going to have to be creative in coming up with a way to compute a similarity score between an image and an audio caption given a match map that somehow captures what it means to be a good alignment. And then we're going to have to come up with a good objective function to train the whole model. So we explored a lot of different ways of computing the similarity between a spoken caption and an image given a match map. And one way that works particularly well is if you basically just make a hard decision for each speech frame, and you take the spatial maximum at each temporal time step, and then you compute an average over the time dimension. So you're essentially saying I'm going to take a max to decide which speech frame grounds to which piece of the image, and then I'll just average over the entire caption. And then that gives me a single scalar score that is differentiable, which I can then use to represent the similarity between a spoken caption and an image. And so then what we're going to turn to is using the triplet loss to actually train this model. So the idea is that I want to have a high similarity between images and the captions that I know go together. And I know that they go together because when I showed somebody this image of this go-kart and these go-kart racers on Mechanical Turk, call that anchor example A, I know that they gave me paired example P as a waveform describing the content of the image. I don't know what words were spoken in P, but I'm assuming that the person followed the instructions and described the semantic content of the image. So I want these to have a high similarity, but in order to prevent the model from just assigning a high similarity to every single pair of images and captions, regardless of whether they go together, we're going to offset this with a contrastive term, where what we do is we just sample imposter waveforms that people recorded when they described other images that were not this image of the go-kart. And so we want those to have a very low similarity. So we can formalize that just with the standard triplet loss equation here with just this gamma margin term, which specifies how much stronger we want the affinity to be between the paired examples and imposter examples. And then of course we can make this symmetric by considering the speech to be the anchor point and then sampling imposter images. So the natural question you might ask is, well, how do you actually select examples, negative examples to do this training? And so we only consider negative examples drawn from a mini batch, and we consider all of the other examples within a mini batch to be potential negatives. And so what we actually do that works a little bit better than just random selection of those negatives is we do negative mining by basically looking for the most difficult negative examples within the batch. And so what that looks like is trying to find the negative examples that have the highest similarity to the to the anchor point. But actually, what we ran into were issues where if you just take the max across all the similarities of all the negatives, you end up with some label noise, because if I have this caption A, which is describing this car point P, then it's very likely that maybe there's some other image that also has a car in it in my mini batch. And so that would be the hardest negative, but maybe it's actually also a relatively good match for the caption. So what we do is we actually we discard all of the negative examples that have a higher similarity to the anchor point than the paired point. And then we only consider the ones that are still less similar to the anchor than the pair, but still maximally similar to the anchor over all of the remaining negative examples. So this is called semi-hard negative mining. So this is the training objective that we're going to use for training these models. And the way that we're going to evaluate the model's ability to match semantically images and captions is just with a retrieval task on a whole bunch of held out images and captions. So the idea here is given a novel caption the model's never seen before and a whole bunch of images from a held out set of images, the model should be able to judge which image the caption is describing. And if it gets when we cast this as a retrieval task, basically we say that the model gets a point if it returns the correct image within the top n examples. And here I'm just going to show retrieval at 10. So basically if the model brings back 10 images and the right one is somewhere within that set of 10, then the model gets a point, otherwise it doesn't. So then this recall score is going to vary between 0 and 1. And we'll do everything in the symmetric direction as well, where we use an image as a query and we're querying captions. So on this testing set with 1,000 held out pairs, random chance is going to be 1%, recall at 10. And if we just train the model that I described right off the shelf, we get about 45 to 50% recall at 10. And if we do a little bit of pre-training, either in a supervised way by initializing the image backbone with an ImageNet pre-trained model, or we do some sort of unsupervised pre-training. In this case, we just took the Flickr videos from SoundNet and essentially trained the model with the exact loss function that I mentioned before we trained it on the spoken captions. We pushed the recall scores up to close to 70%. And the upper bound that you could get with this model on this particular data, we estimate by just replacing the speech with word embeddings of the text transcriptions for the captions, which were estimated with an automatic speech recognition system. And that's about 75%. So we're getting very, very close to what we could do if we actually had a speech recognition system here. So to give you an idea of how these match maps actually look during the course of training, they start off very, very diffuse because the model doesn't know anything about recognizing words or objects or how they should be grounded to one another. But here I'm going to show an animation where I basically take a snapshot at every epoch during training. And you'll see that very, very quickly, this match map tensor converges to something that is pretty stable, which seems to represent a learned grounding scheme that goes across the modalities. And so to better illustrate exactly what this what this alignment tensor looks like, I'm going to now play back the audio for you while overlaying the mask on top of the image. So you'll actually get to see what the model thinks somebody is talking about in the image as they're talking about it.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blueprint dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
Here we see a stretch of grass and a small road leading up to a very old ancient ruin.
A white and blue jet airliner near trees at the base of a low mountain.
So you may have noticed that in a few of those videos, I had color-coded the mask as it was being overlaid on the image. And the way that I did that was basically taking the match map, thresholding it at a minimum value, and then extracting volumetric connected components from the resulting match map. And so what you could imagine doing then is using that scheme to actually do a semantic co-segmentation across an entire data set to try and discover word-like and object-like units and clustering them together. So if you do that across the entire training data set that I used of about 400,000 pairs to train this model, and then you ran your favorite clustering algorithm on top of the embeddings that you get both in the image and the speech modalities, then what you would get is a picture dictionary. So here I'm just going to display a whole bunch of example clusters where I've taken the 9 most central image crops for each cluster, as well as the 3 most central audio crops for each cluster.
Castle.
The castle had
Castle. On the couch. Round couch.
And a couch.
Sunset.
the sunset. Sunset.
The train.
Train.
The train.
Wooden.
The lighthouse.
A lighthouse.
A lighthouse.
So I won't play every single cluster for you. I'll just replace the audio here now with the majority vote underlying text label for the audio snippets. And you can see that in general, you know, these clusters are quite pure and correctly capture, you know, both the visual semantics as well as segment out the speech underneath, and if correctly, you know, I match the visual segments with the word that describes them. And in general, on this data set, our model is learning somewhere between 200 and 500 different words and what they refer to. So now I want to go into the second part of my talk, where I'm actually going to talk in more detail about the emergent linguistic structure that we see appearing in these models, both at the word level, but then going down deeper into the subword level. So if you recall, at the beginning of the talk, when I introduced this learning paradigm, I said that the model would have to implicitly learn to recognize words in speech, but words are also composed of subword units like phones and syllables, and they're also playing a role in a much more complex system where there's rules of syntax and grammar and things like that on top of it. So the question that we want to look at here is, well, what is the model learning in the lower layers of the network if it's able to capture visual semantics at the top of the network here? So what we're going to do is we're going to try and peek into the lower layers of the model, specifically on the speech backbone, and see if we basically get other kinds of linguistic structures for free, such as syllables or phones. So the first thing that we looked at was whether we could just take this, you know, this model sort of as it was without modifying it all and find any particular layer that seemed to be very, very highly sensitive to subword units. So what we found is that the second convolutional layer, if you took the ensemble of all activations within that layer at any point in time, they seemed to oscillate, where they would all kind of fire together, or you'd have a large number of them firing, and then they would all kind of go silent until the next firing. And so on the left, that's represented by the blue curve, and the red dotted lines that I've drawn on top of that curve are actually the ground truth phonetic boundaries that that I've gotten from so I used a data set here called Timit, which has which happens to have very, very fine-grained phonetic alignments for the speech. So this wasn't the data that we trained on. This is just what we're using to do some analysis on what kind of subword unit learning the model has learned to do. And so we see that these peaks in the activations on this particular convolutional layer tend to synchronize very tightly with these phonetic transitions. And if you actually then extract the peaks with your favorite peak picking algorithm from this blue curve, and then you PCA them down into 2 dimensions, and then you color code the points according to the broad phonetic manner class of the left context phonetic segment and the right context phonetic segment, you get this really beautiful sonarans hierarchy on the right. So what this is basically showing is that the model has learned to sort of represent at this layer the speech signal in terms of these primitive vowel consonant and consonant vowel classes. So on the right hand side of the plot, you see the orange, purple, and blue, which corresponds to vowel stop diphones, vowel fricative diphones, and vowel nasal diphones. And then on the opposite side of the first principal component, you see like the red, the green, the light blue, which corresponds to the opposite CVs, so nasal vowels and fricative vowels and stop vowels. And then just in sort of the center of the space, you've got silence and syllabic vowels. And then down here on the bottom left, they're stop consonants all by their lonesome selves because they're a little bit different than other kind of consonant types. They have a little bit more dynamic structure in them. So it was very, very cool to see that the model had basically learned to parse speech in terms of these primitives that would make a lot of sense to a linguist. And so then we thought, well, maybe we can actually use this kind of model as a form of pre-training, not unlike BERT or Elmo for NLP or using sort of ImageNet pre-training for visual tasks. Could we use the features that were learned by this model for supervised speech recognition and get some kind of benefit from it? So what we did is we took the intermediate features learned by one of our models and then just replaced the spectral features in a conventional speech recognition system with those features. So essentially what we're doing is we're replacing the spectrogram inputs with just these features coming from an intermediate layer in the model. And then we're training a standard end-to-end speech recognition system using those features. And so we did that on two different tasks here, Aurora 4 and Timet. And we did that on these data sets because they both have some interesting properties. Aurora 4 has speech from different recording conditions where you have clean speech, but then you've got speech with a lot of background noise. So that could be, you know, like a cocktail party or road noise, as well as a mismatched microphone, and then speech which is mismatched both in terms of the microphone as well as the background noise. And so if you were to only train your ASR system on the clean speech and then test it on all of these different noise and mismatched microphone conditions, you can see in the blue bars in this upper right hand bar chart, your error rate goes from well below 10% to all the way up to 40%, 50% or higher when you mismatch the noise conditions or the microphone as compared to the training conditions. But when instead of using spectral features, you instead use the features which are derived from the intermediate layers of this visually grounded speech model, you can see that the detriment to the performance is much, much less. So those are the gray bars, which basically indicates that these features are a lot more invariant to nuisances like background noise or mismatched microphone conditions than spectral features, which makes a lot of sense because the model must have learned to be invariant to those kind of things in order to be able to infer visual semantics from the speech during the self-supervised pre-training phase. And then we also found that there was a similar effect when you were looking at speaker characteristics. So if you were to only train on only male speakers or only female speakers from the Timet database, and then you were to test on speakers from the opposite sex, then you would find that your error rate was higher on the speakers who were underrepresented in the training set. So again, you see this large increase in the error rate going from training on male speech and then testing on female speech with the blue bars when you're only using these spectral filter bank features. But the detriment is less when you're using these features coming from the intermediate layers of the visually grounded speech model, again shown on the gray bars. So that's also demonstrating that these features have learned to be invariant or more invariant than spectral features to differences in particular speakers' voices. So the next thing that we looked at was whether we could actually explicitly model the discrete structure of subword subword speech units like syllables or phones by putting layers into the speech backbone, which were essentially discretizing bottleneck layers. So here what we took is the VQ layer from the popular VQ VAE model, and we essentially spliced it in between the convolutional layers in the speech model. And the way that we train this is we found that in order to get good results here, we actually had to insert this bypass connection, which allowed the model to bypass the quantizer during the first phase of training. And then we only activate the quantizers after the model has already kind of learned to recognize something sensible from the speech signal. And so this activation curriculum, when we have multiple quantizers in place in the model, actually heavily influences what's learned. And you can read, I'll get into this a little bit later. If you're curious, the updates that we use here for the quantization blocks, this is just from the appendix of this Aaron van den Noord paper from 2017. We found that for our particular case, rather than just using a pure gradient-based update, that actually updating the codebook entries here using this exponential moving average was more effective for our particular task. So now I want to show you what these VQ alignments actually look like when we infer them on a new speech signal. So here what I'm showing is two different spectrograms And then above them, I'm showing the alignments produced by the vector quantizing layers of one of these self-supervised speech grounding models. The green layer is the lower quantizer layer, and then the yellow layer is the upper quantizing layer. And then above the yellow layer, I've also included the ground truth time-aligned word transcription. So what you can see here is that in these two different utterances where somebody said the word train, yellow unit number 248 aligns pretty closely with the word train. And then you can also see I've highlighted in green the shared unit subsequence underlying train between both of these two different speech utterances. And you can see, for example, that unit 358, 306, 908, that seems to align somewhat to this this high frequency noise here that you see at 0.8 seconds on the bottom spectrogram and about 4.1 seconds on the top spectrogram, which is the S sound, or sorry, the TR sound in train. And if we look here at a different spectrogram where instead of train, I've now replaced the top spectrogram with another utterance where somebody said the word trees instead, you see that the word is different, but it still starts with that same TR phonetic sequence. And again, we see unit 358, 306 appearing and aligned to the TR in trees. And you also see unit 358 aligned to the TR frication in tracks on the bottom spectrogram, but we don't see unit 306 there. So it seems to be that what's going on here is maybe the upper layer is learning something that is correlated with words, and the lower layer is learning something that is subword in nature. And so we can confirm that by experimentally or by computing basically a conditional probability table of the probability of a particular phone given a particular unit activation computed across the entire TIMIT data set. And so here dark color indicates a higher conditional probability. And what you see here is now that I've sorted, so I've basically done co-clustering on the rows and columns here to try and block diagonalize this matrix. And you can see that the units tend to group by broad manner class. So at the upper left, you see j, ch, sh. All of these palatal fricatives and affricates are modeled pretty reliably by the same underlying set of VQ unit codes from the lower VQ layer. And then the second block is vowels, and then down to dental fricatives, nasals, stops, alveolar fricatives, silence, back vowels, and so on. So there's a pretty nice structure that we see here learned by the code books in the lower VQ layers. And then we further validated our hypothesis on these codebook entries learning something that's discriminative of across phones by looking at the ABX error on the Zero Speech 2019 challenge. So the idea here is to evaluate different kinds of unsupervised speech representations for the purpose of doing phonetic discrimination. So if you have a whole bunch of evaluation examples which are minimal pairs, so they just differ by one phoneme, for example, beg versus bag, then the ABX error is essentially the probability that the similarity, where similarity here is just computed with dynamic time warping on the feature representations for beg and bag. If you have two instances of beg and one instance of bag, then you incur an error if you say that the similarity between bag and one of the instances of beg is more similar than the two instances of beg to one another. So that's called the ABX error. And the top performing system on this challenge from 2019 was WaveNet VQ, and trained on the zero speech data. It got an ABX error rate of about 20%. So 0 is perfect, 50% is random guessing. When we train it on our caption data set, it actually got worse due to the mismatch between the training data and then the evaluation data here. So that went up to about 25%. But when we took our system, which was trained on the places captions and then evaluated on the zero speech data, we got a ABX error rate of under 15%. So even though there was a mismatch between the evaluation data and the training data, we were still beating the top performing entry from this challenge, which I think further indicates that this model has learned something very interesting and also very discriminative about subword speech units. So we can also look at the word-like learning that's happening here at the upper VQ layers by computing precision and recall and F1 scores between the codebook entries and all possible words in the vocabulary. So we essentially, we compute a F1 score for every single codebook entry by treating it as a potential detector of every single word that appears in the test data. And we say, okay, so if unit 248 was a detector for train, what would its F score be? If it was a detector for car, what would its F score be? And then we assign a score to that codebook vector equal to the maximum F1 score that we find across all vocabulary words for that particular codebook entry. And then what we can do is we can sweep the F1 score threshold across all those codebooks and count the number codebook entries and count the number of entries that had an F1 score above a particular threshold. So I mentioned earlier that the particular learning curriculum you use for these different VQ layers heavily influenced what was learned at the different layers. And so as you can see, those are all the different colored curves here on this plot on the right. And depending upon the curriculum you use, you'll see that a particular layer learns a different number of word detectors. And so we did some further follow-up experiments on this that seem to suggest that that after you sort of start quantizing, the model kind of crystallizes and it doesn't really push the information around anymore. But before you quantize, the model is kind of free to place, word detecting ability or phone detecting ability at different layers in the model. But in general, when we found that a particular layer learned to function as a very reliable word detector, again, we're finding on the order of hundreds of different words recognized by that. By the codebook entries in that particular discretizing layer. And so to give you an example of just some of these detectors and what they look like and what their F scores were, this is I think I'm showing the top 20 and then 186 through 200 detectors from the VQ3 layer here, from the top model in the previous slide. And so again, the words that are being detected here are a lot of the same kind of, visual nouns that I was showing before when we were using sort of post-processing methods to do this kind of clustering. But here now the model is figuring out this this kind of discrete structure just during end-to-end training. So as a bonus, we actually found that incorporating this discrete inductive bias improves cross-modal retrieval. So now we're pushing our scores up to about 80% on the image and caption retrieval task. So the last part of the talk now is going to be going into multilingual training. So the idea here is that if you have a model which is capable of discovering visual objects and the spoken speech segments and words that refer to them in one language without knowing anything about that language a priori, then why couldn't you also collect a caption data set on some other language and train an analogous model for language B, and then use the model to try and figure out which speech segments in language A and which in language B tend to refer to the same kind of visual regions. And then you might be able to use that as a sort of Rosetta Stone to figure out translations between words or phrases directly on the speech waveform level. So what I did is I collected another data set, this time of Hindi spoken captions, also Mechanical Turk, with the same image data set. And I'll just play one of those to give you an example of what they sound like.
एक सफेद रंग की बड़ी इमारत है जिसके पीछे हरे भरे पेड़ पौधे और कुछ छोटे मकान हैं और सामने समुद्र का किनारा है सामने काफी सारा समुद्र का पानी.
So here what we do is we generalize the learning paradigm that I introduced earlier to the setting where now we have two different captions for an image and they're coming from different languages. And so what we found worked the best here is if we actually try and enforce similarity between these triples. So in every single different direction of retrieval that you could possibly consider as indicated by the solid black arrows in the embedding space here, we are enforcing a high similarity. And then we're sampling imposters for every single one of those different 6 directions of retrieval that you could consider. And so when we test this model to do image-to-speech retrieval, recall at 10, and speech-to-image retrieval, what we find is that the monolingual models are significantly underperforming the bilingual model. So the blue bars just represent if you only trained this model on English speech or Hindi speech, how well would you do on this particular data set for the retrieval. The recall numbers are a little bit lower here than I was showing in the past, and that's because the training data set is only 25% as large as the original data set. So we only collected 100,000 Hindi captions for this data set, and so we're only using 100,000 of the English captions here. But when we do the bilingual training, we see that the model is effectively able to leverage this data coming from multiple different languages to improve the recall scores for both English and Hindi at testing time. And then I think even more interesting is when we actually evaluate the caption-to-caption retrieval. So where the model doesn't look at the image, it just listens to the caption in English or in Hindi and then tries to retrieve the corresponding caption in the other language, which describes the same underlying image. So if you don't use the image branch at all, you just ablate that backbone of the model, then that would be the blue bars here. And so you can actually still get better than random chance retrieval going from speech to speech, although it is definitely below, much below what you would get if you actually were able to have that visual information as part of the training. So the orange bars are where we are using the visual information and during training, but then not during retrieval. And so that seems to indicate that the model is definitely able to leverage those visual semantics in order to aid with cross-lingual learning in this case. So we can also kind of generalize this idea of the match map that we examined earlier, where instead of looking at the affinity between a particular speech region and a particular image region, now we're looking at speech regions both in English and in Hindi. And so what you see after you take a trained model and then you compare the output representations for the English speech and the Hindi speech, you get this really cool block structure in the similarity matrix. And if you then take these blocks and you align them to the ground truth text transcriptions, both in Hindi and in English, what you find is that they generally correspond to synonyms or phrases that refer to or mean approximately the same thing. So in this case, I'm showing in this particular example, the words in Hindi for between the sea and the beach here, aligned to the English words for beach and ocean, and similarly with the words for mountain. So what we can then do is we can attempt to build a bilingual picture dictionary by basically using those blocks as regions of interest within the speech signals, extracting them and then clustering based upon the embedded representations. And then instead of just clustering the image embeddings and the speech embeddings in one language, now we're doing these triples all clustered together. So here what we can derive is a bilingual picture dictionary. So I'll just play a bunch of examples from that experiment. And you'll hear the three most central English speech examples and then the three most central Hindi examples for each cluster.
There are many people staying and some people खरीदारी कर रहे हैं.
लोग नाच रहे हैं.
देख सकते हैं चार
Small green tree.
Bunch of trees.
green trees. यहाँ बहुत सारे पेड़ हैं. बाहर बहुत सारे खंबे हैं.
कुछ पेड़ों को देख सकते हैं.
Top of a body of water. The
Picture of water and
Of a lake.
पानी में एक
यहाँ पर पानी ऊपर से आ रहा है. तालाब का पानी लग रहा है.
Playing a guitar.
Beat and a guitar on a
And holding a guitar.
गिटार खड़ा होके गिटार बजा.
एक हाथ में गिटार है.
Industrial kitchen.
small kitchen
In a kitchen.
एक किचन की तस्वीर. बहुत ही खूबसूरत किचन की.
An old woman wearing.
Two women pose.
Of a woman painting.
बहुत सारी औरतें दिखाई दे रही हैं.
एक रेलवे प्लेटफॉर्म देती हुई दिखाई देती है.
So what I've shown today is really just that taking a very simple idea that we're going to take images and speech and try and relate relate them together with a model has actually blossomed into a whole bunch of different very, very interesting, applications, experiments, and learning of different things. So, not just, we trained this model to basically do multimedia retrieval, but we found that along the way, it actually learned to detect objects and words and subword units, and even port this ability across languages. And that these representations that it learned were useful for downstream supervised tasks, such as conventional speech recognition. So to kind of reprise this slide again, I think that there's a lot more open work that we could look at in this sensor-based learning paradigm way down in the bottom right-hand corner of the plot. So we've really only looked at what can we do with still frame images and spoken captions describing those images. But the ongoing work that we have is looking at doing image-to-speech synthesis with this data, learning from videos, both these sort of short action-focused videos with a multimodal moments in time data set, as well as more open-ended instructional videos from YouTube. And we've also collected a caption data set in Japanese, and we have a couple papers out which have shown that you can do trilingual modeling between Japanese, Hindi, and English and get even better results than in the bilingual case. And some other directions that I'm particularly excited about for future work are trying to really develop this idea of discrete unit learning on speech and doing more with it. So I think that we could look at building sort of language models to start with, but maybe even more complex models of language on top of these discrete representations that seem to be keying on words, with the idea that maybe we can get the model to learn to sort of account for more aspects of language instead of just sort of spotting these very visually salient keywords, but also to sort of more formalize the relationship between the subword units and the word level units. So I'd really like to look into sort of building differentiable finite state transducers that learn to map from the subword units to the word level units, and then sort of recognizing that as like a lexicon or someplace where you could then kind of split the model or make it modular and adapt it to new tasks that way. So I'm also very, very interested in sort of learning disentangled representations across multiple different modalities, using language as sort of a scaffold for doing that. So the idea there is that language tends to both specify sort of the particular property as well as the values that property takes that we're interested in reasoning about as humans. So I'd like to see what we can use these spoken caption data sets we're collecting to do in terms of actually learning disentangled representations of visual data to start with. And I think that if you look further into the future, that where I'd really like to take this kind of work is actually in placing it in embodied systems that have the ability to interact with an environment, either virtual or real, with multiple different perceptual modes to garner feedback from their environment, as well as engage in dialogue with multiple other agents, whether they're AI agents or humans, to try and get closer to this ideal of embodied learning, which I think is really going to, I think it's really going to pay off in terms of, building systems that are both very, very useful, but also highly robust and able to learn on the fly from their experience. So with that, I just want to thank you very much for your attention and time today. This is a spectrogram of me saying thank you to all of you. And if you're interested in working with any of the data or models that we've developed, you can find links to the data as well as the code on my website down below. So I'm now happy to take any questions that you might have.
Thank you so much, David. That was great. Let's all unmute ourselves. I'll just try to. Yeah, let's all unmute ourselves and thank the speaker. Okay, awesome. So we have a bunch of questions. I think, more of them on the chat are from the first part of the talk. I think about the places caption dataset. So I think the first question is from Katie. Oops, I'm sorry. Yeah. Yeah, I think that the first question is from Katie. So I'll just let Katie unmute herself. Yeah.
I, I might have missed this, but I was curious on the crowdsourcing spoken images data set, if there's only a single crowd worker per image. And if so, sort of, do you assume that the crowd workers are saying things that are accurate, or did you have any sort of measure of the error rates there? And if there are multiple crowd workers for the same image, how does your model deal with that?
David, I think you're muted.
Yep.
Yeah.
Yeah, sorry about that. So we actually only collected a single spoken caption for each image that we have here, and the reason that we did that was we sort of assumed a fixed budget for the number of captions upfront that we could collect, and we thought, well, would it be better to have a smaller number of images but then multiple captions for each image, or a larger number of images and one caption for each image? And given that we had many more images available than we actually used to do the collection, we opted for the latter for the reason that we thought, well, it would be better for us to have sort of a larger diversity and coverage in the images that the model was going to be trained on. Although, in an ideal world, you would want to have multiple captions per image that maybe correct for errors, but also highlight different things, because different people pay attention to different aspects of the image. So I think it would be very interesting in the future to look into collecting a larger number of captions for each image, and then sort of seeing what are the differences in terms of what people pay attention to, but then how can you leverage that additional information to improve performance. But for now, what we've done is only collecting one image one caption per image.
Did you audit sort of like what the crowd workers were doing at all in terms of like, were most people really accurate and high quality captions?
Yeah, so generally most people were very accurate in what they provided. We didn't do any kind of so the only kind of validation that we did for the data was, for each recording, we verified that it was longer than a particular length in seconds, and I think it was like 3 seconds. And then we also ran a very weak speech recognizer off the shelf on it, where we were doing this on the fly as they were recording. And so we weren't expecting to get a very accurate transcript of it. We were just trying to count the number of words that they spoke, just to sort of prevent people from just clicking record and then clicking stop record and clicking submit. So we just wanted to make sure that they spoke at least 8 or 10 words. And so the validation that we did was all done on the fly. So I think that really helped us in terms of collecting high quality data, because if people just recorded half a second worth of silence and tried to submit it, our application actually wouldn't allow them to submit that, because it was doing this on the fly checking, and it would say, no, you have to record a more descriptive caption. And I think that tended to be a pretty effective barrier for anybody who, I mean, crowdsourcing is notorious for there being, certain people out there who try to scam the data collection. And I think this was pretty effective in keeping them away. And we had thousands and thousands of people providing data for us here, and the overwhelming majority of them did a phenomenal job, and sort of went even above and beyond our expectations in terms of the captions that they provided.
Got it. Thank you so much.
Okay, so now we have a question from Subendu. He posted a question on the chat about semi-hard negative mining, and I think he mentioned another question too. So yeah, Subendu.
Oh, I was not going to ask about the semi-hard.
Oh yeah, sure.
Negative mining.
You can go ahead with your question. Yeah.
Okay. Thanks, David, for that really cool presentation. I had a question about your first model, which was doing this interaction between the audio-visual. So if I recall correctly, you had the image, and then you send it through a convolution network. You had a hidden state, and then you also had spectrogram, which kind of looks like an image, and you sent it through another CNN model, and then you had the final vector. and then you had some sort of a map, and then between those two, and you did pairwise loss with I guess with the similarity score with some scalar. So
Right.
my question is, did you have any transcript at all, or was it only the image and audio that you had for these examples? Did you have any transcript?
So when we did this training, it was only the image and the audio. There was no transcripts being
There's no
used.
transcript.
Okay. The only times, so we did estimate transcripts using a speech recognition system run offline. And that was because we wanted to be able to analyze exactly what was being learned by the model. So we did produce transcripts for this data.
Okay.
And then we used them only for analysis. And then the only experiment that we used them for was sort of in that top line oracle experiment where I replaced the speech with the text to see, well, how well would the model do if it was sort of able to, perfectly recognize the words in the speech. So in that experiment, we did use the text, but all of the experiments where the input was speech, the model did not have any access to transcripts or underlying, orthographic knowledge of those.
I mean, even if it didn't, if you had the transcript available, so this is, I guess, just a suggestion for a way to avoid this whole negative sampling. So one way I think you could ground it is if you get the vector from the audio signal, and then you get the vector from the image signal, and then you use a single decoder to decode that transcription. So it's conditioned on both these things. So that way, it can actually, if you constrain the decoder sufficiently, it is going to learn some semantic relationships.
Right.
So I've done some similar work on doing that with text and audio. So you have a text sequence and an audio sequence, and you produce the same target text sequence. So that way it actually learns to do both of them together. So I wasn't sure if that's something that could help.
Yeah, I think that's actually a very, very cool idea because so it's kind of like coupling together a speech recognizer with an image captioning model.
Exactly.
And you could actually, I think that would be very, very cool to look into, especially in the case where, because that opens you up to the possibility of now being able to do training where you might have disjoint or sort of not completely overlapping data sets. So you could have a bunch of images where you have some captions and, you have a bunch of speech where you have some transcripts, and maybe you have a few pairs, examples where you have all
which are overlapping. Yeah, exactly.
And so you might be able to sort of gain something, the speech recognition capability might be able to benefit even from those training examples where you don't have speech and vice versa. So I think that would be very, very interesting to look at from sort of a low resource, standpoint.
Yeah, okay, cool. All right, thanks.
Thanks.
Okay, awesome. So the next question is from Deep. Yeah, Deep.
Hi, actually I'm meeting David later, so I can hold my question till then. I'll let anybody else go.
Okay, so sounds good to me, yeah. Okay, so the next question was from Ria, but I don't think Ria is still on the call. So I'll just ask it anyway. So I think this was about the second part of the talk. I think you were showing some Timnet clusters out there. So the question is, how are the underlying text labels from these clusters identified?
Right. So the way that we did, so I think this is with respect to the picture dictionaries that I was showing, if I understand the question correctly. Mm-hmm. And the way that I did that was, so the segmentation that I described, where we're doing this co-segmentation across the images as well as the speech, it produces, a mask over the image, but also a mask over the spectrogram. And so you can basically derive a start time and an end time for a particular connected component as it, projects down on top of the spectrogram. And so then what you can do is if you also used, a speech recognition system like we did to derive transcripts for analytic purposes, that also gives you a time-aligned word sequence. And so you can basically then use some interval arithmetic to look at, which words did we maximally overlap basically with a particular mask component. And so we would just grab those words out and associate them with a particular mask. And then within a cluster, then what we did is just a simple majority vote over the words that the masks overlapped to derive the label for that cluster that I showed.
Okay, awesome. So I have a couple of questions myself, but maybe I'll just wait for anyone else who has a question. Okay, yeah, you can go ahead.
Oh, hi.
I'm also curious about the deep question. Why is machine learning is able to localize the objects?
Yeah, so that's, I think, one of the, that's a great question. And I think it's one of the, the coolest aspects, at least, when I saw it happening, I thought I was very, very excited by it. Because, you're localizing something that is not, you don't have this kind of information provided in the, in any kind of like supervision. And I was actually inspired by one of the papers from Antonio Torralba's group looking at class activation maps. And that's where the inspiration for this basically came from, thinking, oh, well, basically they're able to do some kind of localization from a classification task. So would we also see that kind of localization arising from a metric learning task? And it turned out that we did. And I think that if you think about it, it makes sense because in order for the model to judge that a particular, caption talking about a car goes with the image depicting a car instead of an image depicting a chicken or something, it would need to be able to basically, recognize that, well, there's some words referring to the car in the speech, and it would need to be able to recognize the car as opposed to the chicken in the image. And the way that we get that to happen is basically by using, this kind of, these models which directly preserve sort of spatial information and temporal information. So we don't kind of ruin the spatial structure by putting like a fully connected layer on top of it or anything that would require us to do. I mean, you could still probably derive masks, but you would have to use something like GradCam or more complex,
yes,
doing that.
In that paper, they use, the image labels. And I guess, but in this case, I mean, how important is the hard negatives? If
they're pretty important. I think generally, they generally result in something like a 25 to 50% relative improvement in as measured on the retrieval task. I didn't go over it in today's lecture because it's pretty new work, and I haven't published too much on it yet. But other people who have looked at similar tasks with these kind of models and data sets a lot of people were using the triplet loss for doing this kind of metric learning, but have since switched over to using like info NCE and some of these other these other loss functions that actually seem to work a lot better. So anecdotally, I can tell you that if you replace the hard negative or the semi-hard negative triplet loss with info NCE, if you're familiar with that, you'll get slightly better performance than I was showing here, but it will also converge much, much, much faster. So I think you'll see convergence in 15 or 20 epochs instead of 70 epochs or something like that.
Thanks.
Yep.
Yeah.
Okay, awesome. Any other questions? Okay, yeah. So I can go ahead with mine. So actually, the first question also already sort of answered. I was wondering whether like other metric learning approaches like InfoNC will work better than will work better than the triplet loss.
Yes.
Yeah. The second question, I was quite fascinated by the last work where you could like learn mappings between words through vision. I had a higher level speculatory question. So there's a lot of success with these text only models, like those BERT models or the multilingual BERT models. I was just wondering whether like whether there's any active efforts from you or from other groups to like compare the representation that are learned from these text only models and these multimodal models that use speech and vision as a modality and are probably closer to how babies learn language. So yeah.
Yes. So the answer, if I understand you correctly, you're kind of roughly asking if there's anybody who's trying to build a BERT for speech or something kind of like that.
I mean, I'm more curious about like the analytical part of it. Like what are the differences in the representation that you learn in these two different cases? Like whether there's any effort to like quantify it or something like that.
I see. Sort of the multimodal learning versus sort of, I guess, self-supervised mass prediction type learning. That's a really good question that I would say I haven't. So people have, from my perspective, working in speech, what we've seen here is that we're basically able to learn very visually indicative or salient words that are useful for doing retrieval, and then beneath that learn that's sort of the taxonomy of subword units in a language that you need to basically spell those words, and that the coverage there has been pretty strong. There have been quite a few efforts to try and do something BERT-like with speech that only uses the speech signal and doesn't use any kind of other multimodal information. And it's only really starting to bear fruit, I would say, in the past couple months. So there were a couple papers that I think have hit archive in the last couple months, and I think going to be showing up at NeurIPS, looking at basically kind of doing BERT style training on speech. And I believe that what they have seen is they're doing almost all of their learning at the very fine-grained sort of subword unit level. So they're not really yet at the point where I think they're learning like large timescale segments that would cover something like a word or a phrase. But the representations they are learning at the subword level are very, very powerful for doing downstream ASR, especially when you don't have very many transcriptions to train with.
Yeah.
So I think that there could be some very, very interesting synergies between, doing something BERT-like and doing something multimodal grounding-like, and combining those into a similar framework is something I'm very interested in looking at.
Okay, awesome. So yeah, I'll just ask everyone if anyone has any final questions, and if not, then we can we can unmute ourselves and thank the speaker once again. Okay, awesome, cool. So thank you, David. This was an excellent talk, and I guess I'll just stop the recording.